Our next presentation will be by Jean-Michel Guillot, Measurement of Odours compounds with DEVIS based on SPRi technology. Jean-Michel Guillot is professor at IMT, means ALS, the #1 group engineering and management graduate school in France, an institution depending on Ministry of Industry and Economy. Jean-Michel has a PhD in chemistry from the University of Grenoble, France, and has been working on environmental odors for more than 25 years, with main developments on sampling and measurement methods. He is author of approximately 140 publications, with worldwide partnership and collaboration with universities from Brazil, Australia, Italy, Spain, Germany. He is French reference for standardization about environmental odors, and then member of European committees for standardization. He is technical expert for accreditation of laboratories in the field of sensorial measurements.
Okay, thank you. Disculpe, hablaré en inglés porque es más fácil para mí. Okay, so we are going to speak about this new methodology for sampling. So first of all, which one? Okay. Well, we will speak about, of course, always odorous compounds that create an odor. You know, we always mix the two values, and sometimes it's not so good. So what can I say? We always see a kind of comparison between human nose and what we call electronic nose, even if the term is not so perfect. It's still interesting to see something. We can quite easily see the similarity. Of course, we breathe and we use a pump. We have bioreceptors and we can use sensors. You have, in that case, signals that are obtained from your receptors. Generally, here in noses, it's electric signals. And of course, you have a data treatment by human brain or by different algorithm, and so on. What is important, if you want to create an equipment that more or less do the same, of course, you can work on these two main aspects, receptors, because if you increase the number of receptors, like in humans, you will be probably better in terms of sensitivity, discrimination, and recognition. And of course, if you have a very efficient treatment, of course, you will also increase the distinction and the discrimination. That's typically the main lack of instrumental measurement. Of course, actually, the results are not the same, and probably not in the future. Sorry. Okay. So, what can I say about this new technology? The global aspect is very common. You know, you have a pump here, then you have a cell. Okay, I will distinguish exactly how it works. You have a first step with interaction of compounds with the sensors, and then, in fact, the originality that you measure by using a light and recording the interaction with the with a small camera. And of course, you have a data treatment of everything. So this device is developed by a French company that developed everything, you know. And I can show a little bit the detail of how it works. Okay. So typically, this methodology, surface placement resonance imaging, was created initially for liquid samples. So it's applied here in gas samples. So you have, of course, an interaction or not between your sensors and your odorous compounds, or just VOCs. And what is important, that depending on binding or not, you have this kind of image. So you can, in one way, have a view of an odor. So you can have data about binding, specificity, affinity, kinetics, and of course concentration. It doesn't work well. Okay, is this one? Okay, thank you. Okay, this one is better. So if we retain the three main actions of the measurement, of course, you flush the air and you have interaction or not on the surface. Then you light your surface through a prism and you record the image and you obtain typically an image with your odor. So you transfer a chemical sensation into an image. And of course, this image is stored in a database, and you can, of course, train your system, and then you just have to verify this image. It's like a QR code or something like that, in fact, okay? So some results, of course. The advantage of this technology is that you can use a lot of sensors on a very small surface. So with this results, we just show 3 compounds with 10 replicates, and we have 70 different sensors on the surface. So you have a very rich fingerprint, and it's quite easy to see that, okay, these compounds are different because we don't have the same fingerprint. Even if you compare this one, so you have an aldehyde here also with 5 carbons and with 8 carbons. So with classical sensors, it's very close fingerprints. And in that case, you know, this one is quite different from this one. So we can continue to work like that, you know, and we clearly distinguish when we make an analysis in principal components that we can easily distinguish an alcohol from the other alcohol, or even with when we have the 2 compounds with the same number of carbons, you know. So it's very efficient. We can continue. We can also see that it's efficient to distinguish pure compounds from mixtures, and of course from butanol, which is, you know, the reference compound for odor and for olfactometry. So if we continue, we can see that for mixtures and typically for orange and grapefruit, we can also see the difference. And what is important is that even for enantiomers that have typically the same characteristic in terms of chemistry, without optimizing the device, you know, we can clearly see that you have the isomer R in this part and the S in this one. And that's very interesting because typically you know that enantiomers can have different feeling and present different odors. And with GCMS, you cannot do that. Right? You have one peak and that's it. So it's nice for this aspect. Of course, you have some drawbacks. So we'll go on with other results in terms of sensitivity. So typically we compare when we have a sample in a Tedlar bag. So the equipment is like that, so very small. We compare the results with quantification by FID. So first test is just to know the weight, in fact, of each factors when we create a mixture of 50-50 or 75-25. It's a percentage in the liquid, so it's not in the gas phase. But we can see that if we repeat 5 times different mixtures, the main identification is globally due to the size of the compound. So it seems logical, you know, bigger the compound is, bigger it's easy to be trapped, to be fixed on receptors. So it's not so it's quite logical, you know. And typically we confirm this aspect with the size of the compound, because if we look on different families, looking at alcohols, you know, for methanol and ethanol, the sensitivity is very bad. Okay, well, I can say it's not very odorous, it's not a problem, but of course, it's still a problem because you need a lot of quantity. But when you have a longer chain, it's better. You have the same tendency for alkanes, the same for carboxylic acid, even if for these two it's not linear, and also for ketones globally. So the size of your compound is really important. Of course, it's quite a new equipment, you know, it's on the market, but 4 years ago, the first device had the size of 1 cubic meter. So now it's just 4 times a smartphone. So we can hope that we'll have some improvements. So what can we say about this approach? The first point is that with the number of sensors, we increase quite a lot the sensitivity, not the sensitivity, but the selectivity comparing to other instrumental measurement. So you have high potentialities for identification. Of course, the target could be the human nose. We are not at this level, but yes, it's interesting. The quantification is based on optical measurements, so it's very new. Generally, it's electrical signals. And actually, we have some limitations, but you know, because it's an optical system, you can also work on wavelengths and different things to optimize. Typically, I did some experiments with N-butanol with low quantification limit, and the lab, the company who creates the equipment also tried with other wavelengths, and they add a factor 100 in terms of sensibility, just working on the wavelengths for N-butanol. So, you know, it could be better. Last point, of course, it's a very small equipment, totally independent, it's nice. The response is fast. But of course, we still need some improvement. The number of biosensors is very interesting because, of course, you have sensitivity, stability. You can put several times the same sensors on the surface, so you have an internal repetition. Of course, the development is also about treatment and odor database. The objective is to have a better perception of odor by odorants, and of course, to decrease the cost for adaptation of specific use. And that's it. Muchas gracias.
Thank you very much, Jean-Michel, also for the 12 minutes. And now it's time for some questions, the public. Yeah, we have one question here. Aquí.
Thank you for this interesting presentation. One question is about the capacity of the sensor to resist in the environment, yes. But another is the memory effect that you have when you have more using for this in order to detect the new compounds. Normally you have sensor that you have in the time a losses of the sensitivity or a losses of the linearity.
Yes, you can have a drift like all this kind of device, of course.
Exactly. What is your experience in your case?
We in fact the prism with the surface and with biosensors, it's very small things, and you can change it quite easily. You know, so okay, you have to define if you have to change every 2 months or different things. In the lab, we kept, of course, it's experiment in lab, we kept the same cell during 1 year and a half without changing and without a big drift. So for this aspect, it's okay. For external application, obviously, it's not fine. It could be an objective in the future, but obviously you cannot use it now for external sources because, like a lot of sensors, you have an impact of humidity, of temperature. So for that, of course, your result will be very bad. But I think even if you use in for industries, of course, in big plants you have always offices, and you know that you can have some contamination into your offices. So for meeting room, for office, I think it could be typically an application because you adapt to the global odor, and your equipment can always say, okay, what is the air quality? If it smells something or not, because for this kind of application it's better actually for indoor air than for ambient air.
But in your development, your approach is like the concept of sacrifice sensors to using for outdoor?
Yes, no, but obviously for outdoor, we must think of something else, you know, to limit the impact of temperature, of humidity. So maybe to have something just before the pump, you know, to regulate, because if we apply directly, yes, we know that it will not be very efficient. But typically, in fact, at the beginning, the device was developed for wellness, for anosmic people that can have an idea for their environment, and of course for safety also, because typically for anosmic people, they don't know if the atmosphere is nice or bad. So we can imagine typically for indoor air and even in industrial environment to have this kind of compound, this kind of product, sorry. Or maybe, well, why not in this room, you know? we are on the ground, we are several people. Yes, we can see if the quality is nice or not.
Thank you.
Any more questions for Jean-Michel? Yeah, right here.
Which is the cost, more or less, of the device? You already told me, but...
Yes. I think it's, I don't know the exact price, but it's around 10,000 euros. So comparatively to big devices, it's very cheap.
Okay.
After, I don't know the price for the different cells that you can change, but globally, no, it's not too expensive.
Okay, so no more questions. Thank you very much, Jean-Michel. Merci.